Welcome to AutoSens, the world's leading community for ADAS and autonomous vehicle technology development. We create best-in-class events, training, and information in order to connect the global community of scientists, engineers, and other automotive industry experts. One such industry expert has been with us for a long time in the AutoSens family. We're glad to welcome back Mike Dempsey, Managing Director of Claytex. Mike, welcome back. Good to see you again, friend.
Hi, Carl. Great to be here again.
Mike, give us an overview of Claytex and tell us just a little bit more about the company and the work that you do.
So everything we do at Claytex is about modeling and simulation. And essentially the business has two streams to that. One, which is based around a tool called Dimmler, which is all about modeling the physics of how vehicles behave. So that's the engine, the electric motors, batteries, vehicle dynamics, that side of things. But then what is more relevant here to the AutoSens community is the autonomous vehicle simulation side of the business, where we develop a product called AV Sandbox. That builds on the RF Pro simulation environment. And what we're adding to that are sensor models, traffic controllers, all of the tools to orchestrate and execute hundreds of scenarios so that you can really immerse your AV control system into a virtual environment and test it out and see how it works on all of those test cases, all of those edge cases, all of the risky things that you want to know it can handle that you don't actually want to do in the real world.
And Mike, in our last interview, there was quite a bit of an exciting news for you and the Claytex team. We were discussing the Innovate UK government-funded project Sim4Cam Sense. That's Sim4Cam Sense, and that Claytex was leading that in collaboration with several partners. And so at that time, Mike, we talked about the focus on winter testing that was being conducted in Scotland. There were 15 different sensors, including various types of LiDAR and radar and cameras that you had deployed. And then during this testing, you ultimately learned how these sensors can be validated by essentially examining their ability to detect targets in challenging conditions. So following the winter testing in Scotland, further testing was then carried out at an airfield where the same 15 sensors were mounted on a static rig. Mike, can you take us through that? Talk about this additional testing and talk about the purpose of this and what insights you gained and what ultimately were the results when you were testing at this airfield.
Sure. So, I guess first off, the winter testing was all about understanding the effect of weather on these sensors.
Yeah.
And so we collected a huge amount of data doing that work. What we wanted to do then was look at how do we develop the process to validate a sensor model? What does the test work have to look like to be able to prove that the sensor model is replicating a real device? And so for that work, we went to an airfield. So we have a big open space with nothing in the background. And again, we set up our static sensor rig with all of those 15 sensors that you mentioned. So a variety of cameras, radars, and LiDARs. And we were then using simple targets mounted on a robot. And so using that robot, we could move the targets through the field of view of the sensors in a very controlled way. And we could have it stop at particular points. We could have it drive transient maneuvers in front of us. And what that allowed us to do with these simple targets, which were a simple road sign and a radar corner reflector, is measure how the sensor performance changes across its field of view at different distances. And so that helps us then to validate that when we recreate those in the simulation world, we see the sensor performance change in the same way across its field of view. That helps us validate that the basic physics of the sensor models are working correctly. What we also did while we were on that airfield is we took a couple of real cars, fitted them with a robot driver. So again, we could precisely control them and drive them around in front of the sensors. So we had that driving towards us on constant heading lines, driving arcs, driving loops in front of the sensors. And that data is not necessarily about validating the sensors. That's proving that once you've validated them against the simple targets, they also work for more complex targets. And so we did that for 2 real production vehicles. We also took the NCAP guided soft targets, so the crash test target that they use, and we did the same exercise without driving it around in front of the sensors in a very controlled way. Again, to prove that once you've validated the sensor models on these simpler targets, it still works for more complex targets. And obviously picking the NCAP target helps us because then we can demonstrate that all of that stuff you need to do for ADAS testing, we can do using our virtual environment, using our AV sandbox simulation environment.
Mike, the creativity and the ingenuity and the innovation here is just, it's wonderful to hear you talk about this. And I can see you, I can see you light up when you do. How did you decide to go out to the airfield? How did you decide to pick that location? What was it about the airfield that stood out, and why there? Why was that a good place to validate these sensors?
Well, with any experiment, when you're trying to do something for validation, you want as few variables as possible in the experiments that you're carrying out. So really, an airfield is great because there's nothing behind it. You've got this big expanse of tarmac where you can drive around and you can do tests. We went out to about 110 meters, I think was the furthest test that we did. But you have big distances, but then there's nothing in the background as well. So there's nothing else that's going to interfere with your measurements. Although having said that, there were some quite big hares that were running around on this airfield. And so occasionally we saw those in the background and we're like, now we've got to simulate those things. But anyway,
Sure, sure.
the main reason was, that lack of other things that can interfere with us. We have a controlled space, nothing else around, and we can decide what is going to be in our measurements.
Mike, going forward for the rest of the project, what other goals and objectives do you have planned? And maybe if asked another way, what is the overall goal then of what you're working towards?
So the overall goal for the Simfa CamSense project was really to try and answer the question of how do we produce a sensor model that's going to be good enough for safety assurance? And by good enough, that's a pretty vague term in its own right, that things like the EU regulations talk about the simulation being credible. A lot of the sort of safety assurance processes talk about good enough or credibility in the context of the tools that you're using. And so we've been trying to really explore and understand what does that mean. If we are trying to say that we can use this simulation environment to say that an AV is safe within a particular ODD, so it can operate in all these different conditions and all of these different locations, what does that mean to our sensors and our sensor models in particular? So within the Simfa CamSense project, there was a whole work package looking at just the sensor requirements. And so trying to understand from the point of view of an AV developer, if you're going to equip the vehicle with a suite of sensors, what are those sensors and what is the function that they're actually going to perform for you? And really where we were trying to get to was to understand that, okay, we've put this particular LiDAR on there because we want to be able to see what is on the highway for the next 500 meters. So that needs, based on the geometry of a typical highway, you need a 15-degree field of view for that. We need to be able to see at 500 meters, but we also want to then be able to pick up small objects. Like we might want to know that there's a tire lying in the road 200 meters ahead of us so that we've got chance for our, our semi, our big rig to brake and avoid it. So what resolution do you need of that LiDAR to be able to pick that? But really for us as a simulation company, what that cascades into is that our simulation also needs to be able to have that resolution. The models need to be able to replicate that as well. So that has driven a lot of the work that we've been doing and the direction that we're going in trying to answer this question of how do we make the sensor models that are good enough for safety assurance? And I suppose what it also drives is a lot of this test work as trying to understand how do the sensors perform under all these conditions. And so between now and the end of the project, we have a lot more test work that we are planning to carry out. So we will repeat the winter testing that we did last year in Scotland. We are planning to set that up again, maybe not in the same location, that's still to be decided. But the project would clearly like to collect more data with snow involved to understand and have better confidence in that those performance measurements. Another thing that we are looking at is how do we measure the performance of the sensors when they are experiencing road spray. So if you think about when you're driving on the road, it might be raining, but actually the biggest challenge to you being able to see ahead is the spray that all the other vehicles around you are throwing up. And you can get that even when it's not raining. You know, if it's a downpour has been through recently, your view can suddenly be obscured by all of this spray. And so the questions we have are things like, well, how is road spray different to rainfall? Is it different, or is it the same kind of mechanism, but it's just effectively much heavier rainfall? It's a much denser amount of water that's being thrown up. But there's a lot of things that we don't know about that yet. And so we're starting, you know, we've been doing some research trying to understand what is it that we really want to go and answer in these experiments, and how do we go and do it? And I think the biggest question we have is, how do we quantify that road spray that we're looking at? Because it's really easy to go and put some sensors on the car and go and drive it along a wet road and go, yeah, we've measured something. How do we actually quantify that? And because, you know, we're then trying to use this in simulation, we need to be able to quantify it all so we can then feed it into the simulation and feed it through into the physics models.
We've been speaking with Mike Dempsey, Managing Director of Claytex, longtime member of the AutoSens family. Want to encourage all of our AutoSens attendees and viewers to learn more about Sim4CamSense. That's the Innovate UK government-funded project. Sim4CamSense, Claytex is leading that in collaboration with several partners. Mike, always a pleasure to talk with you. Thank you for being with us, sharing your expertise and thought leadership, and look forward to seeing you in person here for AutoSens real soon. Thank you for being with us, Mike.
Thank you, Carl.
For more information on Claytex and to find out more about our upcoming events, see the links in the description. And for more in-depth interviews like this, subscribe to our YouTube channel and follow AutoSens on LinkedIn. In Detroit, on behalf of AutoSens, I'm Carl Anthony.